Cool. Okay. Yeah. So as I say, what I'd like to try and do in this section, I'd like to try and go through some samples, some sample proofs to kind of practice, make sure that we're all on the same page. Jesus, really doing well this afternoon. So what I thought we could do first, I've got one from. The practice exercises. So our first one is one of the practice exercises from page 147. So this is exercise A. It's actually number 4 in those exercises. So it's one that we've only done one example of, but it's proving that some sentences are jointly contrary. So that's our first one. Our second one is showing that these sentences are provably equivalent. And then our third one is just going to be a straightforward proof. But I think all three of them are ones worth going through to kind of, one, to make sure that we're all on the same page with these question types, to see how to play around with some of these quantifier conversion tools, and then think about, well, we'll come to it. This one's a beautiful proof. I love it. Okay. And if we get through these, we'll cycle through, we'll do some more. Right. So let's start with our first one. And I'm going to yell because I want to make sure that the mic picks me up, but we'll hopefully make it work. So our first one again, right? Our first one, we have 4 sentences, and what we want to do is show that they're jointly contrary. So the aim is going to be eventually to prove a contradiction here, right? We want to end in the upside down T. Every time. So we want to end in the upside down T. Now, one strategy point to note whenever you're proving joint contrariness is the working backwards theory isn't necessarily going to be super helpful. Because you know what the last step is going to be in these, right? In every case, whenever you're proving some sentences are jointly contrary, the last step, or somewhere very close to the last step, is just going to be negation elimination. Always, right? Because that's the only way we can get the contradiction. It might be that we're going to generate the contradiction and then move it around by, say, TND or existential elimination or something like this. But you know that broadly this is going to be the very end move. So, what's the strategy for doing joint contrariness? It's actually really simple. It's find your contradiction. Look in the sentences that you're starting with, spot the negations. And then think about how can you generate the unnegated version of those sentences. Does that idea kind of make sense there, right? Because you know you want to get to this. That means you need a sentence and its negation somewhere. So instead of working from the back when you're proving joint contrariness, work from the front. Look and see what sentences you have. Think about where you're going to get your contradiction from. So running with that idea, if we look at these 4, can people start to see where we might get a contradiction? I think because of the size, we won't do Q&A, right? We'll just sort of do me ranting at you. So this is just old man yells at cloud. Sorry, it'll be fine. But if we look at sentence 4 is going to give us our negations. So all we need to do now is see, is there some way that we can get the unnegated versions of these? And it actually turns out to be really easy, right? We don't need both. We only need one. So let's just pick on not QA. Right? We can get QA. how can we get QA? Well, we're going to use 1 and 3. Because the only things that are in the way of us getting QA are the universal in sentence 1, easy, and the conditional. Right? The universal and the conditional. To get rid of the conditional, we need the antecedent. We have an easy way to generate the antecedent. So the plan is to get us to QA, to get not QA out of here, and then we're done. Do we see the plan? So let's do it. So first, we can go ahead and eliminate our universal in line 1. And of course, universal elimination, we can use any name we want, but we want to use A here. Because remember, we want to get QA for our contradiction. Now this has given us the conditional. We're so close to the thing. We just need the antecedent. So now we'll use sentence 3 to give us the antecedent. Now we have a conditional and the antecedent, and we can derive the consequent. 2 steps away from everybody going home. At step 8, we need to set ourselves up to get our contradiction. Please.
We also have used the conditional elimination on line 6. So only QA and then conditional elimination. And then from 5.
So importantly, whenever we do the kind of conditional elimination, you always need to have the conditional and the antecedent. Right? So yeah, we needed both of these. It didn't matter the order that we got them, right? We could have got them in the other order. If that's what you're after.
Yeah, but why did we first have to get the BA?
Good. So importantly, remember, for conditional elimination, you need 2 things. You need the conditional and you need the antecedent. If we had only done this, right, if we didn't do step 6, we cannot get QA yet. Because we know that the conditional is true, we've derived that, but we don't know how. It could be that both of these sides are false. But as soon as we learn that, hey, the antecedent's also true, then we learn, oh, the consequent has to be true. That's why we need both. Okay, good question. Yes?
But I thought that is that in TFL, we don't also prove the antecedent? Or do we need to do that there as well?
Both of them. Always, always, always. Whenever you use conditional elimination, you need to have the conditional and the antecedent, and what you get is the consequent. So it's always, conditional elimination requires 2 sentences, and it gives you 1. Okay, so we get QA. And now remember, the aim was to eventually get our contradiction. So what we want here, we get not QA. And this is easy, because the only thing in the way of us getting not QA is that conjunction. And conjunctions are no problem at all. You just snap it in half, take the conjunct you want. And now we have a sentence and its negation, which sets us up to do the move that we knew was going to be at the very end. Negation elimination. Okay. So, let's talk again, generalizing from this proof. When you're proving joint contrariness, some strategies to think about. Don't really think too much about the working backwards move. because it's not really going to help you much. Instead, think about where are you going to get a sentence and its negation? Where is your contradiction going to come from? Think about the assumptions you're starting with and spot your negations. Find where the negations are going to come. And then think about how you can get the unnegated versions. Yes?
How did you get PA from universal elimination on line 3?
Good. So remember, line 3 tells us, hey, for all y, py, everything in the domain is a p. If everything in the domain is a p, then we can eliminate that universal with any name we want. So we used A. Everything in the domain is a p. So what's one of the things that's going to be a p? Whatever the hell A is. That's what this move gave us.
You have to show that.
No, because we've got the rule, right? The rule tells us if you have a universal, you can replace the universal, the variable, with any name you want. We could have gotten PB or PE or whatever, but we wanted this, to come back to the earlier question, we wanted this because we'd already set ourselves up with this condition. By using A and this one, we can get QA. Yes?
Suppose we get our contradiction the same way through R.
Yeah, nice. That's what I was going to ask next, right? So note, we did it using QA, but we could have done it with RB, right? In fact, it's going to look very similar. It's just going to slightly different notions, right? If we wanted to do the contradiction through not RB, well, what we would do is we'd use line 2, eliminate this universal, replacing it with B. We'd use line 3, eliminating this universal, replacing it with B. Looking very similar. Right? Then do conditional elimination to give us RB. And then conjunction elimination to give us not RB. It is basically the same, just we change some of the numbers and what letters we write. Okay. So again, the thing to take away here, when you're proving joint contrariness, you end in the contradiction. Think about how to get your sentence and its negation. That's the thing to work with. Okay. More questions on this one, or shall we move to the next one? Okay? All right, next one's a little bit harder. So for the next one, it's proving joint provability, right? Provable equivalence. There's the phrase I was looking for. Provable equivalence. So we have two sentences, and we want to show they're provably equivalent. This is also one of the ones from the homework. I think this is on page maybe let's see, I'll look. 148, exercise B. This is the first one from that. So, if we're going to show provable equivalence, how many proofs do we have? Got to have 2, right? We got to have 2. One that starts with the left and ends in the right, and one that starts with the right, ends with the left. Which one do we want to do first? Left to right? We'll do left to right first. So for left to right, we assume the left-hand sentence, and we want to derive the right-hand one. Cool? Now before we dive in, let's plan. Let's think about how this proof might go. So, looking at our conclusion, what kind of things do we think? Do we notice?
It's just the rule of switching negations, right?
Quantifier conversion could help us out a little bit here, right? Quantifier conversions could help us out a little bit here. Because if we think about quantifier conversion, right, the CQ rule, well, we can use the CQ rule on this, and it's going to give us now, how does that help us?
It's not the case that AX and not B.
So let's start to unpack it, right? Let's think about this. Looking at this it's one step away from our target.
Yeah, it was like swap this, right?
So that's the CQ, right? It lets us play swapsies. So if we were going to derive this, what rule could we use to derive this? Well, one option would be universal introduction. Right? And of course, if it was universal introduction, before that we would have that sentence with names in the buckets. The same name in both buckets. To make our life easy, let's use little c. C needs to be arbitrary. Needs to not appear in any undischarged assumption, but so far so good. Now, how would we get this? Well, let's think. What's the main operator of this sentence? It's a negation. So a rule that might give us this is negation introduction. So now, could we get a subproof that starts with AC conjunction not BC?
That ends in a contradiction.
Also, sorry, I keep adding a negation here. There shouldn't be a negation here. It's my fault. Realizing, hang on, this is going to be real hard. Could we get any proof that starts with AC conjunction BC that ends in a contradiction? No problem.
AC, then
We're going to use conditional elimination. We're going to use this conditional to give us our contradiction. Okay, so here's the plan. We do this, subproof, to let us introduce this negation, to let us introduce this universal, to let us CQ it to finish it off. So let's do it. We start off with the sentence we want to negate. We want this sentence to end, this subproof, to end in a contradiction. We want to show that this sentence must be false. So one of the first things we can do, let's take both conjuncts out. We want both conjuncts. One of them is going to be what we're going to get our contradiction with. We're going to use the other one to give us half of our contradiction. At line 5, we can turn back to our opening assumption and we can eliminate our universal. We can replace the associated variable with any name. What name do we want to use? Let's see, the only name we got going. Okay? Now this sets us up because with 5 and 3, we can get not BC through conditional elimination. And again, as we were talking about before, conditional elimination, you need the conditional and the antecedent, and it gives you the consequent. You derive the consequent. Now what can we do? What's set up at line 7? We can get our contradiction. We can get our contradiction because we have a sentence and its negation. And our subproof has now done its job. Because remember, the subproof was designed to show us that if this is true, bad things happen. So we can now close the subproof, use the whole thing to introduce the negation. Every fucking time. So, we introduce our negation. And now here's the really cool thing. Does the name C appear in any undischarged assumptions? The only assumption that it appeared in was here, but as soon as we close the subproof, we have decommitted from it. We don't believe it anymore. We have discharged it. So C is entirely arbitrary. So we can replace C, every occurrence of C, with a universal. Is it X? Yeah. All right. And our last little tiny bit of judo, we've got a quantifier next to universal. We push the quantifier through, and it flips the universal to the other quantifier. Et voila. Okay. So let's talk through again this proof. What we wanted to do is we wanted to start with our left-hand sentence and derive the right-hand sentence. And our idea was, okay, one of the ways we could get this done is via quantifier conversion, and then universal introduction, and then negation introduction. That was the kind of reversed plan. So that's what we followed through. We got ourselves to the negated thing with an arbitrary name. That let us introduce the universal, and then we played quantifier conversion. Okay. Now the thing to note with this one, it is kind of difficult. Right? It's not super easy, but we can figure it out by going step by step by step. Please.
What if we, before the contradiction, so before line 7, introduce an existential, and then we just show that that could also be a contradiction, and afterwards we could just introduce the negation, and we have directly the sentence.
Good. So the thought would be basically like, okay, we could introduce existential x bx. Thing to remember though is that what we need is the existential, all the negated existential. So we'd still need to find some way to kind of get that sentence out. But I like the idea. It suggests, what's another way we could tackle this proof? So we did it where the penultimate step was universal introduction. But how else could we do this one? Well, let's look. Looking at our conclusion. If we just look flatly at our conclusion, what rule would we suspect would be the last step? Negation introduction. Negation introduction. So could we build a subproof? Could we build a subproof that starts with this and ends in a contradiction? If we could do that, we'd be good. And I think this is very close to what you were suggesting. Because actually, that's kind of straightforward.
We use quantifier conversion first.
In order to do quantifier conversion, we have to have a negation next to the existential. We don't have that. Right? So what we're trying to do is generate the negation. But let's think, right? If we know that there is something that's both an A and a B, right? Well, what rule can we use on this sentence? What's the main operator? It's the existential, right? So the joy here is going to be a subproof. And the sub-subproof, the whole design of the sub-subproof is to do existential elimination. So we go, okay, let's use some arbitrary name. And we want this subproof to end in something that doesn't feature the arbitrary name. It's going to look funny because the sentence we're going to get technically doesn't feature the arbitrary name. So we would go, okay, conjunction elimination, conjunction elimination. It's going to look very similar to what we just did here, right? Then we do universal elimination. From 1. Yes.
Oh, that's okay. No,
So basically just imagine this is kind of plugged in place of what we have here.
so we don't have the negation in front of the existential because we want to end up with a contradiction, right?
Yeah. Because what we want to do eventually is introduce it. That's going to be our final step. So we want this sub, because again, we can basically think all of this is line 2, this is line 3, 4, etc., etc., etc. We're just replacing what we have. So we have now A, C, conditional, not BC. We can do conditional elimination to give us not BC on this and this. And then in our sub-subproof, we get our contradiction. Now here is something we have not done, but it's worth seeing. Does this feature the name C? I don't see it. It just looks like a weird ass upside down T to me. This is something we can manipulate using existential elimination. We can drag a contradiction out of the sub-subproof 1 line to the left using existential elimination. And that gives us what we want. That this existential leads to a contradiction, which then means we can introduce our negation. Two different ways to get to the same result. Where we build eventually to do quantifier conversion, or where we aim to just do negation introduction right off the bat. Every road leads to Rome. Okay. Please.
Yeah, because you mentioned earlier that we need two proofs to prove that something is provably equivalent.
Mhm.
We wouldn't be able to do the right part of this without the assumption on the first line, right?
Nope. So right now, no matter which of these two ways we go, right? These are basically just two different ways to do the left to right. Whichever one you write down, I don't care. They're both good. But that's still only half the answer. We are still only Bon Jovi. We're halfway there. We got to do the other half. So let's think about our other half. Let's think about the right to left. How do we do the right to left? So our right to left, we're going to take our negated existential as our assumption. And we want to get to that universally quantified conditional. So let's plan before we dive in. Looking at our universally quantified conditional. Okay. Plausibly, looking at it, our last rule is going to be universal introduction. Makes sense, right? Makes sense. I'll write it over here. Universal intro is the last line. That means that before that, we would need a sentence that looks like this. With the same name in both buckets. And importantly, that name needs to be arbitrary. It needs to not appear in any undischarged assumption. Again, doing okay because there's no names in here. So let's go ahead and pencil in little c. Now, how would we get that?
Could we try quantified conversion?
I like it. But again, let's keep going step by step by step, right?
So conditional introduction.
Very plausible conditional introduction, right? Conditional is the main operator here. We're going to do that in the middle. Now, if this is going to be conditional introduction, that means that we have to have a subproof that starts with AC and ends with not BC. Okay. We see the rationale, right? We're just, again, thinking about it step by step by step. Okay, now where will we get not BC from? Well, it's got an operator, right? So let's think about the last step in the subproof being the introduction rule for that operator. Now, how could we get a contradiction if we had BC? Here is where quantifier conversion is going to help us. Because if we CQ this, it's going to be for all x, not this conjunction. And we can build the unnegated version of the conjunction. So now we start to see how this is going to be built. Let's go ahead and write it up. Our first move. Let's do the CQ. Okay? So we want to make that flip. And in fact, we can go ahead, we can do this in the subproof, we can do it now. We'll go ahead and do it now. We'll eliminate this universal. We can use any name we want. So let's go ahead and just use C. All of this is set up. All of this is set up. At line 4 now, we can enter into our subproof. And remember, I've erased it very helpfully, but our big subproof is designed to let us do conditional introduction. So we want this subproof to start with AC, and it needs to end with not BC. In order to get not BC, we open a subproof. The sub-sub proof is designed for negation introduction, right? We want the sub-sub proof to end in a contradiction. With BC. And we are very close to getting our contradiction. Right? What rule do we need to use here? What do we need to do at step 6? Conjunction introduction. Right. We want to take these two, stitch them together. To give us the unnegated version of what's at 3.
Can't I use a universal elimination and use the Morgan rule?
We could do that too. Different ways to get to the same result. So, again, we've got ourselves to here. We can get our contradiction. Now, this means the sub-sub proof has done its job. Because the sub-sub proof was designed to get us to not BC. And that in turn means that our sub-proof has done its job because it was meant to take us from AC to not BC. Four through 8. And now here's the really nice thing. The name C is arbitrary. It appears in no undischarged assumptions. Because every time we made a belief about it, we eventually got rid of those assumptions. We moved out of the subproofs. So we can end universal introduction. Now, I want to say a few things about this proof. First, do not be scared by how many subproofs we need or anything like this. These are hard, sure, but importantly, the kind of reasoning and rationale to explain why we want to do this is fairly straightforward. It's the same thing we've been doing. You work backwards. Think about, this is the step I want to do last. That means I need to do this. Okay, if I'm going to do this, well then I need to do this. Every step has a reason. Every step has a motivation. Together, these two show that our sentences are provably equivalent. Okay. Please.
How and when do we know that we should use CQI?
Good. So one of the things that's really helpful for CQ is think about what operator you want in the front to be able to use. So for example here, right, it's very hard to use negation. There's not many rules that let you do anything with it. On the flip side, literally, universal is really easy to use. And once you use it, admittedly, then you're right back to I have the negation, but you can get rid of it very easily. So if you see something like this, start to think about, hey, okay, I can play swapsies and then give myself something really useful. On the flip side, and this is kind of stepping again, if you're doing something like this, right, proving joint contrariness, think about getting that negation to the front. Because by getting the negation to the front, well, hell, there's only one rule that uses it, but it gives you what you know you want for joint contrariness. So the general kind of thing is, think about what you need to do. Right? Do you need to build a contradiction? Cool. Let's try and get the negation to the front and build the sentence inside. Do we want to do something else? Okay, let's play swapsies, give myself another tool that I can use. There isn't going to be a hard and fast guaranteed motion here, but there's ways to kind of play around. In this case, it was useful because by swapping, we could get that. And then it just became a process of using this, getting to where we can. Okay. Okay. How are we feeling about the 3 that we've done so far? First one, I feel like everybody got pretty good. Middle 2, maybe less so. Let's talk about the last one then. Let's talk about the last one, then we can wrap up for today. Because you can bet your bottom dollar I'm going to probably ask you one that looks a little bit like this on the actual final exam. This is the kind of thing we should be able to do. So, here we have 2 assumptions. We have this existentially quantified sentence, and we have KD. And the result we want is BD. So we have just two premises and the conclusion. Now, the thing to note, what's significant or special about premise 1?
What's the result of the conditional after the universal?
It is X is identical to Y. Yeah, sorry about the terrible handwriting.
We want BB or BD?
We want BD. Oh, sorry, yeah. This is my beautiful dyslexia manifesting itself. BD, thank you. Otherwise, we're going to have a hell of a time. Okay. So, what's special about premise 1? What's premise 1 say? Maybe to ask the same question slightly differently, if premise 1 is true, how many Ks are there? Exactly 1. There's exactly 1, right? Because this tells us there's at least 1 K and at most 1 K. Oh, and that what 1 and only K happens to also be a B. Do we see how that's what sentence 1 says? So we can see how the reasoning for this proof is going to go. There's 1 and only 1 thing that's a K. Let's name it D. Okay, well, given this, that thing must also be B. The rationale is clear. To actually prove it, it's a little bit difficult. Because what's in the way? What's the main move in this proof going to have to be? Eventually, we're going to get to identity elimination. But what's the big move? What's the big thing in the way? We're going to have to eliminate the existential. We have to go through this existential to get down to the thing we want. It's going to look kind of scary, but actually it's very straightforward. Because once you get through the existential, what's the main operator inside the existential? It's conjunctions. It's conjunction, and conjunctions are easy. And then there's the universal. Right? So let's talk about how to do this one. Right? What we're going to do is the main move is going to be existential elimination. That requires that we use an arbitrary name. We're going to reason about this arbitrary name, and then eventually we're going to get rid of it. But when we get rid of it, it's going to give us what we want. So, our first move is going to be to open a subproof. And this subproof is for our existential elimination. So we plug in an arbitrary name. What name do we want to use? Should we just use little a? little a. Okay. Okay. So there's our first move. It is merely to plug in an arbitrary name. Now, what we want to do from here is we want to start ripping parts out. The first thing we want, let's take that conjunction out, that conjunct. Because there's something in there that we want. And specifically, we want this. Now, why do we want that universally quantified conditional?
Because of the I.
Yeah, because the identity. We eventually want to get to this, right? We need to get to a sentence that doesn't feature our arbitrary name A, and hopefully gets us all the way to BD. And it's gonna be easy. Because what we're gonna do now, at line 6, we're gonna set ourselves up to be able to get to BD. We're going to eliminate this universal. Universal, we can use any name we want to replace the Y. What name do we want to use? Let's use D. Because we can get and that's handy. Because not only do we have this conditional, but we also have the antecedent. Right? Where's the antecedent? It's in sentence 2. So we can get this identity claim. So now, according to our supposition, right, in our subproof, A is identical to D. A is identical to D. And that in and of itself is interesting. But we need it to do one more thing. Because now that we know that they're identical, we can substitute. We can replace occurrences of A with D.
We need to get BA from the 3, and then we can get BD.
Perfect. The one bit that we hadn't pulled out, and one of the bits we hadn't pulled out yet. And now that we know they're identical, and we know BA, we can substitute. So this was, again, coming back to the idea. What's identity elimination? Identity elimination says if you know that two names are identical, and you have a sentence featuring the name, then you can replace it with the other name. But now here's the really neat thing. Does sentence 9 feature our arbitrary name? It's gone. A is gone. So we can extract this one line to the left through existential elimination. We use the existential in line 1, and our subproof for the arbitrary name is 3 through 9. So again, this sentence, this proof, looks kind of terrifying because you have this relatively long existential. But actually, it's very straightforward. You go through the existential using an arbitrary name, you work down to the identity claim, and then it's just substituting until you get the result you want to get out. I will ask you a question along these lines on the final exam. That's why I wanted to do it. Looks scary. It's not. It's not. So, the things to take away. We're doing joint contrariness. You're aiming to get a contradiction. If you're doing provable equivalence, 2 proofs. And if you're doing the rest, don't be scared by having to do subproofs for existential elimination. We keep our heads, we keep it clear of what we're doing, what we're aiming for, it's going to be just fine. So, that's what I wanted to get through. I think that's pretty good. I'm pretty happy with that. What we will do in the upcoming tutorials is we're going to keep working on these. Yes, please. Yes. So this one was from page 151, exercise A, number 9. Okay. So yeah, we're going to keep working on this stuff in the tutorials. As a reminder, the next lecture is just review. So come with any questions you have, things like this. Don't stress, it's going to be just fine, guys. Have a lovely rest of the week. We'll see you all again soon.